Let's now go to a more intelligent way of creating a LAN using a more intelligent device instead of a hub, which we call as a switch. So what I have done here is I have gone to these network devices, the switches, and from here I have picked up a simple switch. It has only 6 ports. Let's see. Yes, it has only 6 ports. And as you can see, each of these ports will have a MAC address, just like every port of any PC or a computing device will have a MAC address. So this switch also has a MAC address for each of its ports. Basically, the network interface cards, there are 6 network interface cards. Here there is every PC has a single network interface card, which is a MAC address. Anyhow, I connected this. It takes a little bit of time for the switch to boot up and all. The other switches that are here, it will take much more time because it has more ports. For example, this has, I think, 26 ports and all that. So I have taken this simple switch. We'll now visualize that compared to what is called hub, how the switch behaves. Again, all these have been rebooted. They are all these ARP entries, ARP entries are all 0. Nothing is there. So if you start sending a data packet or data, whatever message, let's see what happens in a switch, how it behaves differently than a hub. To understand this, we'll have to understand that a switch is a layer 2 device or a data link layer device. Why is it called a data link layer device? Because it has the ability to direct traffic based on MAC addresses. Basically, every switch contains something called as a MAC. So this is the GUI interface. Similar, but there is a command line interface also here. Okay, so here you can enter, for example, show MAC address table. You can see the MAC address table is empty. Now let's see what happens when we decide to send a packet. Okay, we decide that we will send a packet from this PC. Okay, we will ping this PC2 just like before, and we are in simulation mode, and let's give it 1. So once again, an ICMP packet could not be sent because the destination MAC address is not available. So an ARP process has been created. So let's look. It reaches the switch. Data frame has reached the switch, which contains its own source MAC address. And in the destination MAC address, what will it have? All F. So it's a broadcast packet, a broadcast frame. But the switch is clever. It realized that in this port, this MAC address is connected. So it populates its MAC address table. So let's see now what its MAC address table says. See, in its port or interface FA0/1, it now has tabulated that this MAC address is connected, this particular MAC address. sorry. This A400, that MAC address is the device having that address is connected to this interface. Now let's see what again happens. It floods it because the destination in the ARP packet was all Fs or all ones if you convert to binary. But it was searching for this IP address. So only this PC accepted it. Rest did not accept. Let's see now what happens. It reaches, it sends an ARP reply message. When this happens, let's say the MAC address table once again. It realized this MAC address of this PC, a device with certain MAC address, is sending data on this link F11. So it populates its table. Now, what happens? Let's see. Now it does not, unlike a hub would have flooded this packet on all three interfaces. It already knows that this packet should be forwarded to this interface. So now if we go again, now ICMP packet will be sent. There is no issue at all. The switch knows where on its switch interfaces these two PCs are connected. And these two PCs also have their ARP message. Now there is something called as a spanning tree protocol. We'll discuss about it briefly, but it's not very important here. So you got the point, what is happening. Now let's see. Let's make again this, see when an ARP, a ping message was done from this PC to this PC, the switch learned that this PC with a particular MAC address was on this FA01 interface. Similarly, FA2,1 interface it learned. So these is the current MAC address table situation. Suppose a PC3 sends to PC4, then the switch will learn the entire network's MAC address. Let's see, for example, let's stop this. Let's see, PC3. Ping 10.1.1.4. Let's do this. Okay, I should have given only one, but anyways, does not matter. So if we go ahead, initially what happens? The destination that it gives is ARP FFF, so it floods to all the members, all the clients it is host it is connected to. But then it learns, for example, it learns now PC4 is connected here, PC3 already it learned. If I look at the MAC address table now, it's already full. It knows all the interfaces and all the PCs with the different MAC addresses it is connected to, which interface has which MAC address, which has learned the entire network very quickly. Now let's continue. See, Now the next few packets, there will be no issue at all. So now let's see what happened here. So whenever there is a broadcast, the address is broadcast in the link layer, FFF is provided, it floods the packet to all the hosts it is connected to, everybody in the network. So it has a single broadcast domain. But how many collision domains it has? A switch has as many collision domains as the number of hosts it is connected to, as the number of ports it is active. In a hub, there is only one collision domain. But in a switch, there are, suppose in this case, 4 ports are active. Only 4 ports or interfaces will be having collision domains, that individual collision domains. There can be no collision because of this PC for this PC. This PC cannot cause a collision to this. This PC cannot cause a collision to this. But in a hub, any PC can cause a collision to any other PC. So let's see this. What do I mean? First of all, we should remember that if these are full duplex links, there is no question of collision. But in certain cases, if these are half duplex links, only then collision can occur. So based on that, we are saying that assume that these are half duplex links, that the switch is having here 4 collision domains. So we'll see what that means. Let's see PC2 and PC3, all pinging PC1. Let's do that. So PC3 is there, and PC2 will see PC2 and PC3. So desktop, let's do ping, and we'll give only one time. Okay, similarly, fine. So both of them want to ping, and both of their ARP cases have, I guess, oh, in this case, it does not have, does not matter. Both of them will send data to the switch at the same time. What happens? No collision. The switch buffers the frames. And then let's see what happens. In one case, because there was a ARP message was there, so FFF was in the destination field, it was sent. Next, there is one packet and another there. It is sent now. So it buffers the frames and sends them one by one. There is no question of collision. So let's now try this again, because last time you saw that PC3 did not have that knowledge of the MAC address of PC1, but now it has. Let's see what happens now. It buffers the frame. One of them it sends. Let's see which. From switch 1, it sends from 3. Source IP address 3. The other one from 2, it has buffered. Let's see. See, now it sends 2. And because it is a full duplex link, so when it sends, it can also receive. There is no question of clash. So if there has to be any collision, it will happen here, 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 and here, where there is half duplex links. When there is half duplex links, in this case, all are full duplex. How do you know? You can see here, config full duplex. If you change it to half duplex, you can investigate on your own what happens. Similarly, config, if you go, I am sure full duplex. If you make it half duplex, it will become different. So this is how a switch operates based on a MAC address table, which it learns by a forwarding algorithm. So now we can talk about what is called VLAN. Well, it's a little bit more complex. So we'll make a different video on that. But the thing is, when it gets a broadcast traffic, it sends it to all. Suppose these two were in a particularly different department and these two in a particularly different department in a office. So what should happen is, if this guy sends a broadcast message, it should only reach here, not the other two. Similarly, this we can do by virtually segmenting this physical LAN into 2 virtual LANs called VLANs. In fact, you can see here in the switch, all of them have a VLAN identifier. VLAN, it's all are one. Indirectly, the physical LAN is the same as the VLAN. We can tag them with different VLANs so that broadcast traffic remains within your own department. So we can segregate this LAN into 2 different LANs by software. So in that case, currently this is having single broadcast domain. But if we are able to segregate into 2 different virtual LANs, this network will have 2 broadcast domains. The number of collision domains will always remain 4. So that's it. We'll talk about VLANs in the coming, we'll demonstrate it in the coming simulations. Okay, thank you.